Welcome everyone to another OTP Tab call. This is call number 152. It's my pleasure to introduce Erza Varaish. Erza is a system and network researcher working at the intersect of distributed systems, high performance networking, and machine learning infrastructure. He recently completed his PhD in computer science at Purdue University, where he focused on rethinking network transport and collective communication to improve performance and resilience of large-scale distributed ML workloads. His work has been published in leading venue, including NSDI, OSDI, IEEE CAL, and IEEE SNP. And he is currently building systems and infrastructure for scalable AI platforms. In today's talk, I will present OptiNIC, a domain-specific RDMA transport designed for distributed machine learning at scale. The work explores how relaxing traditional reliability and in-order delivery guarantees can reduce tail latency and improve throughput across large GPU clusters. The talk will also cover how OptiNIC shifts loss recovery into the ML pipeline while preserving standard congestion control, and will share evaluation results demonstrating significant improvement in time to accuracy, throughput, and tail latency across public cloud environments. Please join me welcoming Erza.
Thank you so much, Ahmed, for the great introduction. I think that covered like the whole gist of what the talk is about. So yeah, thank you so much for that. So hi everyone, my name is Ertza, and I'll be presenting my work on OptiNIC, which is a resilient and tail optimal RDMA NIC for distributed ML workloads. And like Ahmed said, the main insight that we're focusing on is trying to relax the 100% reliability guarantees that the traditional transports provide, and then see how we can exploit that and use it for making large scale machine learning faster, more efficient, more reliable, and more resilient. And this project was a joint collaboration between Purdue University, VMware Research at Broadcom, and the University of Michigan. So I think this goes without saying that we are at a point in time where the modern ML workloads no longer fit onto a single GPU anymore, either because of memory constraints or time. So the only option really is to distribute that workload among multiple GPUs, all connected through some kind of interconnect. For example, training GPT-4 required like 25,000 GPUs to work together. And this is what it kind of looks like, where we have Jensen standing here for scale, and you can see how massive the whole infrastructure and cluster is. Now, the question, of course, is how do you actually distribute training or inference on these multiple GPUs? And to answer that, there are basically quite a few different ways to do that. And I'll focus first on some of the most popular ways. The most common one we use is called distributed data parallel, in which the data set is actually divided among the multiple GPUs, and they each have a complete copy of the whole model. Then we can have something called a model or pipeline parallelism, where the model is divided onto multiple GPUs. This is especially important when the model is so large that it cannot fit into the memory of a single GPU. So what you do is you divide it onto the multiple GPUs, and the output of one GPU is basically used as an input to the next one. And the communication in this case is send receive. So whatever is the output of this goes as input to this. So they are doing this like peer-to-peer send receive with each other. Then we have tensor parallelism, where a single tensor itself is basically divided among multiple GPUs, and the resulting communication can be all gather or all reduce, depending on how you basically slice this tensor. Recently, with the advent of these MOE models, another popular parallelism is this expert parallelism, where the experts or subnetworks of this bigger model are distributed onto the multiple GPUs, and again, the resulting communication can be all gather or all to all. Now, the focus of this work is to accelerate all of these types of communication that can happen in this distributed deep learning scheme, either in inference or training jobs. And to do that, we basically need to understand the relationship between the computation and communication lifecycle of training or inference. So we can start with the data parallelism to see how these things work. Like I said, in this mode, the first step is to just copy the model onto all of the GPUs, and the data set is then divided among them. So each of these different GPUs get a different chunk of the data set, and they start training on that. Each worker node basically locally trains on their part of the data set, which includes running a forward pass to get some output, and then a backward pass to get the gradients for updating the model based on the actual versus expected output. So these gradients are signals to the model which tell it how to tune itself, and this is basically how the model basically learns. Now, since we have multiple GPUs and everybody's running its own forward pass and back propagation step, now before updating the model, these gradients that we got from the back propagation, they need to be communicated among all of the nodes, and this communication is usually done through an all-reduced collective operation which synchronizes and aggregates the model gradients across all of these nodes. This computation and communication cycle keep happening for each batch of data, and the batch keep repeating for a number of epochs. So this all reduced communication, it happens around thousands to hundreds of thousands of times in the modern ML workloads, and it can have repeat a lot of times during the life cycle of training. If you look at the time series, this is kind of how it looks like with multiple of these operations happening. And if you notice here, I've started this all reduce before the back prop is fully done. Like right here, when you see there's this overlap happening. And this is because modern ML frameworks try to overlap this communication with computation to do as much communication hiding they can do to kind of alleviate the bottleneck of this communication. So as soon as even some of the gradients are ready, they are sent out to be all reduced and the communication starts. Still, this all reduced communication is known to take around 65% of the total training time. And I'm talking about this blocking time here, not the time that overlapped. So even that is taking a huge chunk. But now this 65% number was from 5 years ago. And with the advent of even stronger GPUs that we're getting every year now, with some really aggressive compute optimizations like these lower precision things, the compute time is further reduced by a lot. So the forward and backward pass, they get more shortened, but the communication time is still the same because no major innovation has happened on that side in these like 5 years or so. So this has turned the communication into a more critical bottleneck, and it is taking a much bigger chunk than just the 65% that was previously stated. On top of that, at the scale of the things and how these can run in cloud and shared data center environments where many workloads are running in parallel, competing for the same set of resources. And when you have this large scale, there can be a single slow worker or a single delay in communication on some link, which will basically cause everyone else to wait for this one single straggler. And this inflates the tail by a huge degree. So we ask, can we optimize the communication in a way that can eliminate this tail effect and mitigate the effect of stragglers? So to do that, we begin by looking at the compute architecture optimizations that have been done for the past century or so, and we try to draw some parallels with how we can do the same in communication. For example, we went from CPUs to GPUs for faster compute hardware, and similarly, we drew a parallel and did the same thing for communication, and we went from a basic NIC to an RDMA capable smart NIC that can take some of this responsibility into the hardware and do it much faster, similar to how the GPU takes off some of the computation from the CPU. But for compute, we soon realized that only introducing these stronger GPUs was not enough, and it was basically not feasible enough to keep making it to be fair. You reach some hardware limits, and it's really hard to match the growing compute needs. So instead, how we optimize it is we exploited ML's resilience to loss and introduced concepts like doing lower precision compute. And this resulted in significantly faster compute. And the idea was that ML is already probabilistic. It's a probabilistic science. It's not 100% exact. So some information loss is entirely acceptable. Now, all of the new GPU architectures are being designed with this insight in mind. If you run full precision, they'll probably perform very similar to the previous generations. And it is only at these lower precisions like FP16 or FP8 where you really start to see the difference between a newer generation GPU and an older one. So in OptiNIC, we propose to follow the same principle for doing this communication optimization and exploit ML's model resilience, and use this to propose a best effort RDMA transport, which includes a complete redesign of the hardware itself. The idea is that we implement a best effort transport, and we have a strict time bound to mitigate the effect of stragglers and tail. So we only keep whatever arrives within the allocated time window, and we just move on with the partial data, which automatically eliminates the tail effect. Now, the question, of course, is can we actually apply this insight to all sorts of parallelisms and their resulting communication patterns? Are all of them resilient, and can all of them actually sustain their accuracy in the face of drops and losses? And we did empirical results and tests to verify this behavior. And we ran an inference job with the pipeline parallelism and injected some deliberate drops to quantify this relationship between drops and accuracy. So I'll just briefly go over these plots here. We basically are seeing three different models here: DeepSeek, Gemma, and Llama. The y-axis here is the accuracy, and x-axis is the network drops that we're injecting ourselves. So the idea here is to actually inject the drops and see how the accuracy starts to degrade after some time. We can see, I think it's quite evident that up to 1%, all of the models across all of the data sets, they performed marvelously. And there was no significant drops, and I think even up till 5%, there's some really slight variation in the accuracy. So this really like kind of shows you the resilience of these ML models, and I think it comes down to the fact that these large scale models carry so much information, and they have so many parameters that even if some of the information is lost, it is fine because they're carrying so much redundant information. And this basically translates to why we have these ultra quantized 4-bit and even 1-bit model coming nowadays. I saw the 1-bit model the other day, which they said is optimized for like IoT CPUs or something. So they're able to like cut down a lot of the things. And then we have other techniques like layer pruning, where they basically cut the model by half or something, and it's still able to perform similar to the original model because there's so much redundant information going on. So we take this insight and use it to design our new hardware accelerated transport for ML, which basically prioritizes speed over ensuring 100% reliability. So now we look at the current RDMA design and why it fails to deliver. So RDMA is basically used in modern ML clusters to meet the 100 to 400G link speed requirements because when you run it in the kernel stack like TCP, it cannot saturate this bandwidth of 400G links. So the two biggest problems with the RDMA are its reliance on PFC and the go back and retransmission mechanism. And they are basically closely tied to each other, which I'll go over in the next few slides. But PFC is already well known to have a number of issues that can cause PFC storms, deadlocks, and even congestion collapse. For those of you who are not familiar with PFC, basically RDMA was designed for InfiniBand networks, and now in modern ML clusters, it's usually the Ethernet is the underlying network of choice, and Ethernet is lossy, and InfiniBand was lossless. So PFC basically makes your Ethernet lossless, but it comes with a bunch of caveats and problems, which have been shown that it can even cause like congestion collapse, and the network can just stall with a deadlock. So this PFC, which is kind of required for running RDMA in an optimal state, basically halts the network. So these two things are the main thing which cause like a significant drop in RoCE's performance from the median to the tail. And the tail basically occurs whenever you have some drop or some congestion in the network, then everything gets paused in case of this RDMA. And if anything gets dropped, then they do go back and retransmission. And what that means is if packet number 2 is dropped and you had already received packets up to packet number 10, you basically retransmit everything from packet 2 onwards. So you always start from the last drop packet and you retransmit everything. So this is basically the go back and retransmission. So, of course, a lot of the recent works have tried to solve these issues. One of them was IRN. It solved this by implementing a reorder buffer in the hardware. So this basically allows the sender to do selective retransmission instead of the go back n mechanism, and the removal of this go back n basically alleviates the need to do PFC. So you don't need to make sure that the network is lossless because whatever is dropped will be selectively repeated and it will be selectively sent just like we do it in TCP. So this added buffer solves that problem of doing go back n, which severely inflates the tail latency. But this added buffer in the hardware severely limits the scalability of IRN, and we're now basically down to just supporting 8K queue pairs. This is basically the reason why RDMA did not have such a buffer in the first place, because it severely limits your scalability and how much connections you can open with others. So SRNIC tried to further solve it by removing all of this retransmission logic and all of the reliability logic from the hardware, and it basically moved it to the software and simplified the data path as a way to make it much more scalable. So this actually does allow SRNIC to support twice as many connections, and it's now up to 20K compared to the 10K of the original RoCE design. But again, the issue with this is that the inclusion of slow path makes it suffer from very long tail, as those frequent control plane decisions have now been onloaded back onto the host CPU. So if you look at these efforts, you can see that everyone is basically trying to solve the reliability problem one way or another, and they are trading off between long tail and scalability in the various of these designs. What we argue is that ML models are inherently resilient, and in compute and in different layers of the stack, you're already exploiting this resilience. You're already taking advantage of this thing that ML models are resilient, and you're designing the architectures with that thing in mind. So we say we should do the same when we design the communication and when we design the actual NIC. So based on that, in OptiNIC, we basically completely get rid of all the retransmission related machinery from both the data path and the control plane. And this basically results in a significantly lighter and simpler design with much better tail performance. But it also has the added advantage of making the design much more simple and scalable. And that allows us to scale to up to 80K connections compared to the 10K of the original RoCE design. And this is without any performance degradation. Now, to see how we can actually implement this design, we need to look at what the current RDMA already supports and how we can add the support for our connection type in there. So in place of connection types, RDMA calls them queue pairs, and there are many different types of queue pairs. The main three ones that are included, I'll show them here. The first one is RC, or reliably connected, and it is basically just like TCP. So it's connected and reliable, and it offers in-order delivery, and it has congestion control mechanism, and it also supports this offloaded chunking and segmentation in the hardware, which is basically the whole point of doing RDMA transports. So you give it a large message, and the NIC will take care of segmentation and packetization based on the available MTU itself, and you don't have to do any of that in the software. On the other end of the spectrum, we have unreliable datagram, UD, which is just like UDP. It's unconnected and offers none of these things. A simple fire and forget transport, just like UDP. And since it is unconnected, it also does not support this offloaded segmentation. So you only give it one message equal to the size of MTU, and it just fires it, just like UDP. So next, RDMA also includes another combination of these features, which they call UC. So UC is unreliable connected. It does not have any reliability or congestion control, but it does offer offloaded segmentation due to being connected, as well as it guarantees in-order delivery, which kind of basically works against us here in this case, by the way, because any dropped packet will cause all subsequent packets to get dropped as well, as they will be out of order for the NIC. So it doesn't really help us here. We don't want this. So we propose a new combination of the same four design features and call it XP or Express Path. Like I said, the main idea is to exploit the loss resilience. So we don't want it to be reliable. We don't want it to retransmissions, because ML models are inherently resilient against some loss. And we also don't need in-order delivery, as the application does not require it. So it's fine if some of the packets are missing. We just need to directly place them in the correct offset into the host memory buffer. However, we do include the offloaded segmentation so that we can fully utilize the capabilities of a hardware transport. And we also include the congestion control mechanisms. And there are basically two reasons to keep this congestion control here. First, we don't want to exacerbate the loss for us to beyond what is naturally occurring. Like I said, beyond a certain point, the accuracy does start to get dropped. So we want to make sure that we are balancing the trade-off between accuracy and speed. So whenever we have some choice, we need to make sure that we try to keep the losses to a minimum, and that's why we have the congestion control in there. And secondly, the second reason for having the congestion control is so that we only use our fair share of the bandwidth of the network, as there can be other workloads and users sharing the network. So it doesn't make sense to hog all the resources and make it unusable for other workloads. So how do we actually build this transport? So the architecture is basically built on these three design pillars, as I call them. I will briefly introduce them here and then go into the details of each. Number one is a self-describing packet. This is for handling the no retransmissions and out of order delivery. Second, we introduce bounded completion semantics to ensure forward progress despite losses. And finally, we introduce a decoupled congestion control mechanism that works without any reliability guarantees. So now let's start with the self-describing packets, and I'll just dive into the design. Is there a message in the chat? Yeah, I'll probably see this at the end of the chat. I'm not familiar with this work. Yeah, okay. So if we look at these self-describing packets, the main idea and how we contrast is in the current or the vanilla RDMA design, only the first packet of a message basically carries the address for the placement of the packet, and the rest is just inferred from the packet sequence numbers. And the design has some strict assumptions that all packets should come and will come, and they will arrive in order. And in OptiNIC, we basically change this model and relax it. And we propose that every packet should just carry its complete address in the packet and be self-sufficient. It should not rely on some other packets to arrive before it. So if you look at the vanilla RDMA, this is kind of how this works, and it will also like shed some light on why it has these strict notions for everything arriving in order and everything arriving on time. So like I said, the first packet right here is carrying the address info. We append it to the header, and when it reaches the NIC basically parses it and starts maintaining the state for this message. So it stores the base address of the message in the receive buffer, so it knows what's the base address in the host memory, and then it has an offset to write the next packet to, and then the expected packet sequence number. And each time a packet comes in, it basically matches the packet sequence number, and if it matches, the NIC directly DMAs the contents of the packet to the offset from the base address. Once it DMAs, it increments the offset by actually the length of the data that was DMA'd. So it knows the next packet that comes in, I have to write it after wherever this packet number one ended, and as well as it increments the PSN by one. So it knows the next expected packet sequence number now is packet number two. But now if a packet gets dropped inside the network, for example, this packet number two, it gets dropped and the next one arrives directly at the NIC. So packet number three arrived. The NIC will basically check the PSN from the header and compare it with its own expected PSN. And since they won't match, the NIC will simply drop this packet as it does not know where it should place this packet and what should be the offset for this packet. And similarly, all subsequent packets will be dropped as well until the time this packet number two is retransmitted and that arrives at the NIC again, where it will then be DMA'd and the table will be updated to then expected packet sequence number three, and three needs to be retransmitted again, and four needs to be retransmitted again. And this can happen like multiple times. An even extreme case is when the packet number itself gets dropped. So all the address info is just lost. Then there will be no base address or anything to even begin with. And hence all the subsequent packets will get dropped until packet one is resent. And this is basically like why we have the retransmission mechanism as go back N, because the receiver is simply dropping all subsequent packets after a dropped packet. So they all need to be retransmitted again by the sender. They cannot have like a selective retransmission type of thing. So OptiNIC basically changes this design to include the complete address info to each of the packets. So now each packet is carrying the complete address info. And if you look at the even the extreme case that the packet first, the first packet itself has gotten dropped in the network, even then, whatever packet reaches the NIC, it is carrying the full address, the base address, as well as the offset, which will help populate the state table. And you just place the packet directly at the offset and you DMA it into like the correct offset of what that packet belongs to. This basically fulfills the transport semantics of RDMA communication, which means not requiring the CPU to get involved at all. So you can see that there was no involvement of this remote side or host side CPU, and it is able to do this direct data placement without relying on any retransmission mechanism or in-order delivery requirements. Now, one natural question here, of course, might be regarding the overhead of adding this to every packet, but it is small enough that some vendors are already doing this. For example, ConnectX 6 and 7 onwards, I think they now include this option to do selective repeat. And the only way to do this selective repeat retransmission is to have this header in there. So they're already including this in some new additions, but it only, I think it works with the RC, the reliable connected queue pair, and it's not supported for any of the other ones. So the reason why, of course, they did it is that so that the NIC can start placing out of order packets into the correct buffers instead of dropping them, and so the sender has to only retransmit the actual dropped packets and not the ones that come after it. Okay. Yeah, okay, yeah. Perfect timing. I just saw like there's a message, what is the overhead for storing the address? Yeah, yeah, that's the thing. It's small enough that it's I don't remember the exact maybe it's like 20 bytes or something. It's in the paper. I don't remember the exact value, but it's small enough that the vendors are already introducing this. So it's not like a big thing that this we are proposing and nobody else has done at the time. Okay, so the next thing is the bounded completion semantics. In the traditional RDMA design, the completion is basically tied to receiving the complete data, and the guarantee provided by the transport is that it will retransmit on loss and it will ensure complete data is transferred without any bound on the time it may take. In OptiNIC, we again changed this model, and now the transport guarantees time-bounded delivery. So instead of guaranteeing completion of data in unlimited amount of time, we now guarantee that the time will be bounded no matter how much data is transferred. Of course, we have some like internal or inherent semantics to make sure that the loss stays within 1%. But if we just look at the design of the transport, the main thing that we focus on is making sure that it's time bounded. So this basically has, again, two advantages. First, it ensures forward progress in the face of losses because in the current design of how applications are written, they expect that 100% of the data will come in and only then the application can move on. So this allows us to do forward progress without waiting for that 100% of the data. And of course, it has the added advantage of mitigating the tail effects because we're bounding the time, so any stragglers and any tail effects are automatically mitigated. So if you look at the sender and receiver, this side is, imagine this is the sender, this is a receiver, and we have the OptiNIC. And whenever we do a send and a receive request, whenever it is posted to the NIC, we also provide a relative timeout to the hardware, which basically dictates the time window that is allowed for this operation. So both NICs set up that time window for the request, and then the flow starts like any RDMA NIC. The sender starts by DMAing data directly from the user buffer into the NIC, which is sent over the network to the other side. The receiver NIC then directly DMAs it into the receiver buffer, and this keeps going until the time till all the data is received or the timer expires. So imagine this receiver or receive window is where the timer expired. At this point, the NIC basically stops DMing any more data to the user buffer, and it also drops any subsequent packets that come in for this specific request. Similarly, it will just mark the request as completed into the this buffer, and the application basically waits on that completion, and it constantly reads this completion in the buffer from the memory, and it can move forward when it sees that the completion has come from the NIC side. Similarly, on the sender side, when the timer expires, it's the same thing. The window has expired, so we stop pulling any more data from the user buffer and also mark the request as completed into the buffer. So both the sides have timers, and they have their independent timers. They move on without requiring any kind of synchronization mechanism, simply moving on when the timer expires. And the timeout value is controlled and passed directly by the application. So this application is the one who is responsible for maintaining the timeout, keeping track of the timeout, and we make them adaptive, so they are dynamically changing with the underlying network conditions and infrastructure conditions. So to keep a track of all of the different timeouts, I just need to introduce one small thing here, which was hybrid parallelism. So with all of the new LLMs and their sizes and how they are deployed, There's a lot of the times they are deployed with this hybrid parallelism structure where it is a combination of different parallelism schemes, like I discussed previously, that we can have pipeline parallelism, data parallelism, model parallelism. How we deploy them is a combination usually. So for example, if we have six GPUs, GPU 1, 2, 3, 4, 5, 6, we can have pipeline parallelism between sets of three and data parallelism across the two larger groups. So this is what it would essentially look like. And then inside each group, we'll be doing the send receive collective, and across the group they'll be doing the all reduce collective between the corresponding GPUs. So you can see that a single node, for example, this GPU 3 can be involved in multiple different collectives. It is doing all reduce as well, it is doing send receive as well. So it needs to keep a track of all of the different times for the different collectives, and each different type of collective can have different number of participants in that, what we usually refer to them as a group, and they'll each have a group ID assigned to them. So for that, we basically store a timeout map on each node, and it basically stores, it has the key as the collective type and the group ID, and the value is basically the timeout, and it only basically tracks the collectives it participates in. So for the updates, then each node basically share its suggested timeout based on how much data it received in the given amount of time. It if it received, for example, 50% of the data, it can say like double the timeout. This is too small. If somebody finished early and there was ample time left in the time window, it can inform that okay, the timeout is too large. We can have like a stricter time bound. So everybody shares this timeout with everybody else, and then we basically pick the median value to ignore the stragglers and the outliers, because if somebody is slow or somebody is too fast, we ignore them. We just pick the median and then do one standard deviation, so that there's some room uh, for the different variations. And then of course we do the exponential weighted moving average, so that we have a smooth update. And another reason for this EWMA is that some groups can have just one node, and that node can become a transient straggler. So if we just apply the update directly, there's no median because it's just one or two nodes. If we just apply the update, it will be very jerky and the updates will not be smooth. So that's why we do this EWMA smoothing here. And that's basically how the timeouts and the bounded completion semantics work. Finally, we look at the decoupled congestion control. In the traditional RDMA design, the congestion control mechanism for some reason is like strictly tied to reliability of the transport. And from the existing queue pair connection types that RDMA supports, this congestion control is only enabled for the RC type, which is the reliable connected. In OptiNIC, we basically change this model and we treat congestion control as an independent module. And we show that the design of the current congestion control algorithms already allow you to do so. So congestion control mechanisms, what we saw, were like inherently decoupled from the reliability mechanics, and this is why OptiNIC is basically compatible with all existing RDMA congestion control schemes. And I have a dedicated section in the paper covering this in great detail. But as an example, I will show how DCQCN works and why it can work with OptiNIC, which is in running in this unreliable mode. So imagine this scenario where the sender is sending some data to the receiver. When the packet reaches the switch detects that its internal buffer is getting full. So it sets the ECN bit in the packet and forwards it to the receiver. The receiver reads this ECN bit and detects that there is congestion happening in the network. So it immediately sends an explicit congestion notification packet back to the sender. And as soon as the sender receives the CNP packet, it slows down, which is basically the whole point of congestion control, that you throttle the sender and it slows down. Then that's basically the whole flow of how DCQC and congestion control works. Now you can see that reliability does not play a role anywhere in this design. And on top of that, these switches basically ensure that this ECN marked packets, they are sent out before the queues start getting full and packets need to be start getting dropped. So it's all relying on the switch, and it just marks the packet, it sends it, forwards it to the receiver. Receiver sends an explicit congestion notification packet, and it's not tied to reliability in any sense, and hence why we say that it can work out of the box with OptiNIC. And this is DCQCN is one of the algorithms that we used in our end-to-end evaluations, and it worked perfectly fine. So with this, we complete the core design of OptiNIC. But while these three make up just like the core part of it, OptiNIC also includes several optimizations for sustaining the model accuracy by mitigating the effect of losses. So up till now, we were trying to balance and minimize the losses and also exploit on the losses. But we also have some loss recovery schemes that we can use to basically mitigate the effect of those losses that do occur. So in other various domains, we have schemes like Erasure coding and XOR based schemes. But for ML based collective communication, Hadamard transform is kind of the most suitable and has been shown to work great for quantization and lossy transports for ML training before. And the main reason is its homomorphic properties. So any computation and communication can be done on the encoded data itself without decoding it first, which of course saves you precious compute cycles. What happens in all reduce type of communication is that you have data, you send it to someone, they sum it up or they do some arithmetic operations on it, and then they send it to you back. If you employ any of the other encodings, you would need to encode the data, you would need to send it over the network, and the receiver would need to decode it before doing any computation on it. With Hadamard, you don't need to do that. They can do any computation on the encoded data, and due to its homomorphic property, the data that was encoded will also see the same arithmetic operation on it. So I'll give a brief example of how Hadamard helps with drops. So just imagine we're sending some data. We have this vector of 8 here. The first step is just to encode this data with Hadamard, and we get some vector with different kinds of values here. The main idea is that each of these values is now embedded in each of these values. So so each of these values is being represented by each of these single value. And once this encoded data is done, you can send it over the lossy channel, and you can imagine there was a tail drop. So in a normal scenario, this would mean that we just lose this value and we get a zero. But because we first encoded it with Hadamard, we can now decode it and we will be able to recover a close approximation of the sent value. So instead of this 4.5, we get this 4.6 value here. If we had not decoded it, this would just have been zero. And the loss is basically spread over all of the other nodes, so all of the other entries in the gradient. So for example, for this 4.5, we got 4.6, for 1.0, we got 1.9, for 1.5, we got 1.4. So what this loss did is that it nudged the values of all of the other nodes, all of the other gradient entries. But that's the thing with ML. You don't need to be precise. Zero hurts you much more. But if it's just 4.6 instead of 4.5, it's already probabilistic enough that these small changes don't hurt the accuracy at all. And this property has like practical implications for lossy training. For example, we deliberately draw 5 and 10% of gradients when training this VGG19 model using data parallel training. And the pink line here is basically showing the accuracy without applying this Hadamard. So it's just normal case with drops. And you can see that the accuracy drops significantly. For the 10% drop, it's close to like 50% now. But for the Hadamard enabled case, even with 10% gradient drops, the model is still approaching the target baseline accuracy. Anybody have any questions so far? Okay. Okay, so like Hadamard works great for training and all reduce, but for inference, we do have to tweak it just a little bit. And the reason is the overhead of Hadamard. In data parallel training, all reduce calls usually happen on these smaller buckets of data, which are just tens of megabytes. But now with all of these different parallelisms and moving beyond gradient buckets, the collectives can be carrying hundreds of megabytes to even gigabytes of data per call or per collective communication. So the encoding that we do with Hadamard will cause significant overhead because the Hadamard overhead is not linear with size and it's more so exponential. So how we tackle this problem is we divide the full buffer into these smaller blocks and then apply Hadamard to each of these blocks serially. So we can also do this in parallel, but we do them serially, and I'll show the results for this, and I'll show you what's the difference if we do one big operation of encoding this whole thing and the difference between encoding these in small blocks. Now, once we get all these smaller encoded blocks, we can send them out. But if you put the complete block into a single packet and that packet gets lost, then there is no way to recover that data with Hadamard even because the entire encoded information has been lost. So it basically defeats the purpose of even applying Hadamard in the first place. So what we do instead is we spread the Hadamard encoded block over multiple packets. So some part of it goes into packet 1, some into packet 2, some into packet 3, and so on. And each block basically contributes to every single packet. So now each packet is carrying small portion from these multiple blocks, and if a packet gets lost, we still have the remaining information for that Hadamard block from all of the other packets. And we already saw that Hadamard is very good at recovering the missing entry using information from like the rest of the blocks. Now to show like the compute overhead that I was telling you about, so here y-axis is basically the computation time and x-axis is the number of splits that we did. So this is the full buffer with number of splits one, we did not split it and it took around I think 22, 23 milliseconds. And then we started dividing it into smaller blocks and applied Hadamard to them serially. So again, I want to emphasize here that we're doing this in like pipeline. So we encode one, then the other one, then the next one. But still, you can see like with 64 splits of like 2 MB buffer each, it's around 3x faster compared to applying it to the full buffer. So this is kind of like the insight where we were able to do this because we know that Hadamard's overhead increases exponentially. So if you make the value really small and do it a number of times, that's still faster than applying it on the bigger chunk. And now just to see that it's like functionally equivalent to applying the Hadamard on the full block, we have another plot here which basically shows the mean squared error and the network drop rate. So the red line shows no encoding scheme, the purple one is Hadamard applied on blocks, but no spreading over multiple packets. So you got the block, but you sent all of the block in one packet. So that's why you get some like worse performance and the error is higher. Finally, we have this green and blue lines, which are virtually indistinguishable here. Green is for Hadamard applied on the full buffer, and blue is for the block plus spread design that we just described. And you can see that we achieved the same level of resilience as with the original block design. But the advantage is that now we're paying a much smaller cost in terms of the compute overhead. Similarly, this next plot shows how increasing the spread of single Hadamard to multiple packets is better. The first line with this lightest color shows the case when each packet gets 256 bytes from each block, and the darkest line is one where we have just 4 bytes coming in from each block into each packet. And of course, the more you spread a block, the more resilient the overall system becomes. Now on to the end-to-end evaluations. For evals, we basically implemented OptiNIC to work on top of existing RDMA NICs like ConnectX 6, ConnectX 5, ConnectX 7, and we basically turned off all existing control plane logic and implemented our own in software. So this allowed us to evaluate OptiNIC on top of existing NICs, making them compatible with cloud environments and deployable immediately. We also implement an FPG prototype to understand the resource usage and the resiliency of the actual OptiNIC design compared to the baselines. For the test environment, we actually use Hyperstack, which is a known public AI cloud. They provide you with a bunch of different kinds of GPUs, and we tested with 8 H100 nodes. The metrics we report are time to accuracy for the training runs, and for inference, we report the throughput, the time to first token, and the attained accuracy. And just to reiterate, this is what the environment setup looks like. We have 8 H100 nodes, and they are connected using RoCE V2 RDMA over 200 G links. So we start with the time to accuracy plots for the training runs, and we ran it for various models, including Llama, DeepSeek, and Phi. And we ran this training using 0-3 parallelism enabled and used the deep speed toolchain for it. Across all of the models, we can see that OptiNIC is much faster from the get-go, and it is able to reach the same convergence accuracy. If you can see in all of the different models, we're able to reach the same accuracy as the baseline system, but it is much faster. In fact, it is around 2x faster compared to the baseline RoCE. Similarly, the inference throughput also shows significant gains for all of the different models. We ran the same three models, Llama 5 and DeepSeek, but we also included this 30 billion MOE model, Qwen 3, with expert parallelism. Again, for the throughput, OptiNIC is around 1.6x faster compared to the baseline. And the accuracy for all of the models remained similar across both RoCE and OptiNIC for the different models as well. Meaning we're not sacrificing anything for this speed up that we're getting over the baseline RoCE system. Now, for inference, what matters even more than the throughput is the initial latency and the responsiveness of the model. And the measure used for this is time to first token, or TTFT. And this is the latency that the end user sees for any request. So if you look at the mean, then OptiNIC is already around 30% faster compared to RoCE. But when we look at the tail time to first token, that's where we see OptiNIC really shine. And it is as much as 3.5x faster, making it much more responsive to the end user. We also conducted some collective level benchmarks to show the communication benefit without any of this computation overhead. So this basically shows the latency to complete different collectives with varying message sizes. We included all reduce, all gather, and reduce scatter. And we can clearly see that as the message size increases, so does the benefit of OptiNIC. So similarly, when you get like larger models, the benefit gets more pronounced, and we are as much as 2.5x faster for these larger messages. If you see this green box here, we included this OptiNIC hardware. So what we did, we emulated a hardware deployment of OptiNIC by basically subtracting the overhead of running our control plane in software. And we saw that when we compare with that, the hardware deployment was around 3x faster compared to the baseline RoCE. And we also compared OptiNIC against several of the recent ML transfer proposals, including Falcon, UCCL, SRNIC, and IRN. And we cannot include this, unfortunately, in the end-to-end evals because they're not cloud compatible or they don't have an open source implementation yet. So we had to use a simulator for these runs. We fixed the message size to 25 megabytes and recorded the collective completion time for all reduce, all gather, and reduce scatter. Also, the runs were repeated 100 times so that we can get the average and the P99 times. Again, you can see OptiNIC is much faster than all of the transports, even on average. But again, where it really shines is for mitigating the long tail latencies, and it finishes around 3x faster compared to the baseline. And the reason again is that the average and the P99 for OptiNIC is really close to each other, whereas it severely inflates for others. So this mitigating the tail effect is really where OptiNIC shines. Next, we look at this FPGA prototype results, and we just evaluated the scalability and the resiliency of OptiNIC compared to the baselines. So we start with the NIC state, and basically by eliminating all the retransmission machinery and in-order delivery guarantee machinery, OptiNIC basically eliminated all of the state, and we just require 52 bytes of state per queue pair connection. And this allows us to, of course, scale much better. We scale 8 times better than the baseline systems, and we support 80K connections without any performance degradation. Similarly, OptiNIC reduces the lookup tables required for our design, as well as it uses 64% less BRAM, which then directly translates into better energy draw, better power draw, and better resiliency. And this means that the mean time between failures for OptiNIC design is now around 2x more than the baselines. So what that means is that the same cluster, when running with OptiNIC, can run a training or an inference job for twice as long without incurring any faults compared to the original baseline systems. And to summarize, implementing reliability continues to be a major challenge for today's ML transports, and it is hard to design and ends up taking a lot of real estate in the NIC as well, which is completely unnecessary from the point of view of ML. So OptiNIC capitalizes on this ML's resilience to loss and designs this best effort time-bounded ML transport, removes all reliability semantics, which makes the communication 3.5x faster for distributed ML collectives, and it almost doubles the NIC's mean time between failures. Thank you for your time, and I'll be happy to take any questions now.
Wonderful. Thank you very much. All right, let's open the floor for questions.
Can I ask a question, Ahmed?
Yeah, go ahead, go ahead.
So there was a paper about reimagining RDMA that you published before,
Yes.
but you introduced another system. You call it, to the best of my knowledge, Cerebus or something, right?
Yeah, it was Solaris. Yes.
Solaris, yes,
Yeah,
Solaris.
yeah.
Yeah. But what is the difference between Solaris and OptiNIC?
Yeah, that's a really good point. The Solaris was kind of like the motivation for this work. So Solaris was more of like a position paper, you can say, where we had the idea that we'll do something like this, but the actual implementation or the actual design of the system that came with the OptiNIC. So Solaris was it was kind of like a position paper, you can say, for this work. But
Okay.
this work
And
is directly built on that. Yes.
correct me if I'm wrong. It sounds like you are using some sort of coding to avoid um, uh, timeouts and retries to for uh, uh, to support reliability. Am I wrong or right?
Yeah. So we have like I said, it's similar to how you have error recovery schemes in like networks and other aspects of the different domains where you do XOR-based encoding or some forward error correction, FECs-based schemes. So we use this Hadamard encoding, and it's not just proposed by us. It's we kind of use it, but it has been already being used by different communities in the ML for different aspects, but nobody was using it like on the network communication side, but they were using it for lossy compression and lossy transport when they were doing it in the software. Like in my previous paper, we introduced the idea to use it with like a UDP type transport, but now we had to change it somewhat for implementing it for the inference and for doing it in the hardware.
Yeah, so that proves the point actually that you can use network coding to avoid what people usually do to support reliability, which is doing timeouts, retries, right?
Yeah,
Go back in, and window. All these things we studied many, many years ago in
yeah,
computer network books. You are avoiding all of this,
yeah.
correct?
Yes. Yeah, that's kind of the whole point. We want to, because those are the things that lead to the tail.
Yeah, I think this will be very good because you are right. ML systems are more tolerant to losses.
Yes, exactly. Yeah, I
Yeah,
agree. I
good.
completely
This
agree.
is the main observation. This is very good observation, actually.
Yeah, it's kind of like where you have like with video conferences, when it started to pick up, people suggested like why not use UDP and some unreliable transport, because the main idea is the frame should be new and it should arrive in time. It's fine if you skip 2-3 frames in between, but it should not be like that old frames arrive later on. So it's kind of similar that we want to exploit the domain specific property of ML, and since you're doing it everywhere else in the stack, you're doing it in the computation layer, you're doing it in algorithms. The only place where you're not doing it and you want that place to be 100% reliable is the network. So why are you putting like so much pressure on the network where it can also exploit the same kind of resilience and same kind of properties that the other stacks in the ML pipeline are doing?
Thank you. My last question. Uh, do you need any sort of synchronization between CPUs and OptiNIC or GPUs and OptiNIC?
No.
No,
We don't need any
exactly.
synchronization. Yeah.
Exactly. Thank you very much. I'm done.
Yeah. Thank you so much.
All right. Any more questions?
And
So,
uh,
go ahead.
there's a couple of questions. First of all, are you aware of the work that was been done by Ken Berman's group at Cornell on Ditrecker, which I think has a lot of similarities to what I'm seeing here?
No, not actually. Yeah, I think you also shared the link, right? I'll
Yes,
try
the
to
link is
see.
there. All right, and we should talk privately. I've got a lot of connections with people who are solving these problems in SmartNICs. And the one thing that you should be aware of is there is an official OCP project that's called Open Atomic Ethernet,
Mhm.
which specifically addresses this problem of tail latency without timeout and retry.
Oh, okay. Yeah, I would love to connect. That would be really great. I would love to know more about that project and the other thing that you're talking about. Let me also save that.
So I'll put my email in the text, so we should connect.
Okay, perfect. Yeah. I'll reach out to you. Thank you. Thank you so much, Paul.
You're welcome. It was by the way, your talk was fabulous. I really loved it. I'm so glad that I saw this because you really have some deep insights. It's wonderful to see.
Oh, perfect. Thank you. Thank you so much. Thank you, Paul. It means a lot.
Great. Any more questions? Maybe I can throw one question. Even though you mentioned, like, again, we don't have dependency for, you're not looking for synchronizing, let's say, CPUs or GPUs or NICs or, like, the whatever system timer. And so
Yeah.
the question is, would you be able to take advantage of those if they were available or not?
That's a good question, actually.
I mean, what I'm sensing from this whole thing is this is more a reactive thing. You're looking
Yeah.
for the packets. The packets going and coming is like you receive the packet, you transmit the packet, and your order is basically based on these queues. Versus you have schedules that you send things and you don't. I don't know. I mean, it really depends if you have a different mechanism to take care of a proactive versus a reactive. I don't know. So
Yeah, no, I think it does make sense. Like there is something to it. That at least it's a nice food for thought, I think, and we can think of how we can use that to our advantage because it may make a lot of sense. Because there were some works where like they do like streaming aggregation just to make sure that you're sending them out at these frequent fixed intervals and you're sending the data out and it doesn't matter what's happening on the other side. But that actually led to some uh, nodes getting like out of synchronization and some other stuff. But if we have some mechanisms, we're able to like keep them synchronized or they're able to share some information or something. Yeah, I think there might be some interesting inside there. But yeah, I'll have to spend some time and think about it.
yeah. Well, another nugget to add to it is
Mhm.
we often look at synchronization, let's say for the NICs across the network, and that's why like you have all these protocols and efforts and work streams and you name it. Like basically the NICs taking care of all of this, which is great. And I think on top of it, if the switch also comes into the picture, then you may be able to have more gains by scheduling routes
Mm,
rather than you have the switch takes care of
mm,
the imbalance of queues with
yeah.
buffers. Instead,
Mm,
they shouldn't be. I always say this expression. It's like buffers should be treated like bumpers in your car. You should not use
be using
bumpers, but when it's needed, they come to
yeah.
to soften the blow, basically.
Yeah, that's a good that's a good analogy. Yeah.
Yeah,
For this project, like we try to keep it like cloud compatible so that we don't rely on switches.
absolutely.
So
Yeah,
we
yeah.
were not even thinking like what can we like achieve with that. But of course, I think once if you think about like adaptive routing and things like that, which can like which the switch can support and help us,
Yes.
I think that will of course make it much stronger.
But I mean, adaptive routing is the switch tries to figure out things reactively,
Yeah,
But
yeah.
what if the switch and the NICs, they're all treated all together? Basically, you have a time aware network, not just time aware NICs.
Mm.
And even though I mean you have boundary clock, transparent clock, it's still like a time aware NIC world. It's
But
not like a time
but
aware network.
would it be something like circuit switching, where you so for example in ML you know that at fixed interval after this much amount of compute time there will be communication happening and it will use this route and
Yeah, yeah. Circuit
you
switching is the goal.
yeah
Like
yeah
it's the asymptotic thing toward, but you don't want to do circuit switching. You want to
yeah
do
yeah yeah
still
of
like
course yeah
packet
but I'm
switching.
thinking like at the abstract level that's kind of what it comes down to like you
That's
know
right.
the constraints, and you know the timing, and you know how much data will go and what links it needs to go through.
Exactly. Yeah. And I mean, you have another extreme sitting on this edge, which is SONET, and
Yeah.
you don't want to go there either. So it's very interesting.
Yeah. Oh, definitely. For sure.
All right. Any more questions? Okay, hearing none. Again, thank you very much for your great presentation. And we'll see everyone in 2 weeks by presentation from Nicolas Kiro from Oregano, which is a company of under Meinberg. All right. See everyone in 2 weeks.
Yeah.
Bye, everyone.
Thank you so much.
Thank you.
Thank you.
Thank you very much.